In part 1, we generalized how to, this is section 1.2, part 2. In part 1, we generalized how to deal with this fraction in the exponent. And we determined that n to the 1/2 is equal to the square root of n. Okay, and we should have noticed that we can generalize that to a to the 1 over any power is equal to the nth root of a. So the denominator of our exponent becomes the index of our radical. Okay, so that's what we should have noticed in your turn 1. Okay, so now we're going to use that generalization and our power of power properties from our properties of exponents to look at what if the numerator isn't 1? What if the numerator here is not 1? Okay, for example, and we're going to look at it 2 different ways. Okay, so for example, this first method, we have a, again, to the m, there's my numerator, over n, there's my denominator. So what we're going to do is we're going to split up that fraction to 1 over n, there's my denominator part, times m, which is my numerator. And this m could be written as m over 1, because if I multiply this straight across, 1 over n times m over 1, I get m over n. So we're just kind of splitting that fraction up into the fraction and then the whole number. Okay, since it's a multiply here, we can use our power of power rules. Okay, because if I have a base of a to the m times n, that's the same as a to the m times n. So we're going from this and we're rewriting it this way. Okay, so here we have the multiply, because again, a to the m to the n is equal to a m times n. We're going from this guy because we've got that going on. And then now we're going to rewrite it. So my 1 over n's right there. So my missing exponent here is the m. But from our previous work in this section, we know a to the 1 over n is equal to the nth root of a. So we take the nth root of a, and then when we're done with that, take it to the m power. Okay. Another way, oops, sorry, didn't mean to turn the page. Here's method 2, is if you notice the difference between these two, the difference between this one and this one is the order. Here I did the m first to the 1 over n. So my 1 over n is now in my exponent, is now the second exponent, and my m is now the first. So the first thing we're going to do is take a to the m. You notice this is inside this is our radicand, and then take the root. Okay, so first here we do the exponent, first exponent, then root, then we do the root, the square root, and in this one over here, we do the root first, root first, then the exponent. Okay, there are 2 different methods, and really what the numbers are, and if you notice it's a perfect root, is really going to determine which method you use. So here I want you to go ahead, your turn 2. I want you to play around with this and simplify it. Okay, and which method did you use and why? All right, so here is just strictly a box of our definitions that we just got done discussing. So any a to the 1 over n power. So if you have a fraction in your exponent, it's a root problem. It's a square root, it's a cube root, it's a radical problem. Okay, if I have a fraction without a numerator of 1, it's a radical and an exponent problem. And it doesn't matter if I do the exponent first or if I do the radical first, they're still going to get me the same end result. So we're going to do a bit of both now on some examples. Okay, so if you were having a hard time with your turn 2, after we get done with these examples, then you can go back and look at it. Okay. Example 3, we're going to evaluate each fraction. So here I have 9 to the 3 halves. So my fraction is a 2, which tells me I'm taking the square root. And I notice that 9 is one of my perfect squares. So I'm going to square root first. So I'm going to write it as the square root of 9, then to the third. So again, this 3 goes to that 3, and this 2 is the index on there because it's the denominator. The denominator is that index. So I'm taking the square root of 9, which I know is 3, and then now I need to take that to the third. So now I actually took the square root of 9. If you notice in this very first step, I didn't actually change any of the numbers. The 9 is still there, the 3 is still there, and the 2 is still there. Again, we just don't write it. Okay, I suggest in your very first step you do that. You don't actually take the square root. So now I took the square root of 9 and got 3, because 3 times 3 is 9. And then 3 to the third, if I'm not sure, multiply it out. 3 times 3 times 3, 9 times 3, 27. So I get 27. Okay, next one. Okay, first thing I notice, my denominator here is a 3, so that tells me I'm dealing with cube roots. I don't know my cube roots as well, and you might not know your cube roots as well, so I'm going to save and do that last. So I'm going to go ahead and I'm going to do my 8 to the second first, and then take that to the 1/3, or take the third root of 8 to the second. I can do 8 to the second. 8 times 8, 64. So I'm taking the third root of 64. Now I need to figure out, is 64 a perfect cube? So I'm going to play around with some numbers. I'm going to try 2. 2 times 2 times 2. 2 times 2 is 4 times 2 is 8. So 2 to the third is 8. Oh, I should have did that first because that's 8, but that's okay. 3 times 3 times 3, we just did. That's 27. 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is, and go ahead and do that one. 16 times 4 is 64. Ooh, so 4 to the third is 64. So the cube root of 64 is 4. Okay. All right, this next one has a little tricky bit to it. It's got that negative. Again, that negative exponent does not make anything negative. Remember, that takes the reciprocal. So that negative part tends to confuse me a bit. It might confuse you. So let's go ahead and let's save that till last. I know this 2 tells me I'm dealing with the square root. So I'm going to do, and 4, I know how to take the square root of 4. So I'm going to write it as the square root of 4 to the, don't forget the negative, to the negative 3. The square root of 4 is 2. So I have 2 to the negative 3. Well, that negative exponent is taking the reciprocal. So instead of 2 to the negative 3, it becomes 1 over 2 to the 3. And we just did 2 to the third right here. 2 times 2 times 2 is 8. So this becomes 1 over 8. And again, notice how I work down the page. That becomes 1 over 8. Okay, next one is part D. For part D here, your guided notes are wrong. It's missing a part. It's supposed to have this extra minus 125 to the 1/3. So I want you to go ahead and add that to the problem because I'm going to be doing the problem that way. Okay, so first of all, we have 64 to the 2/3. Well, it tells me here my index is 3. Order of operations, I can't do the subtraction yet until I deal with these exponents before subtraction. So I know from a previous problem, I know that 4 to the third is 64. This is a third root, so I'm going to do my third root first. The third root is 64, then to the second power. Again, all my same numbers are there. Before I do any work, I'm going to go ahead and do the next part. Here I have, again, third root, so I'm going to do the third root of 125. So we know the third root of 64 is 4. So I have now 4 to the second minus, okay, third root of 125. This ends in a 5. So there's a good chance it's 5. So let's go ahead and let's multiply 5 out. 5 times 5 is 25. 25 times 5, we don't know, is, 125. So that's 5 to the third. So that would give me 5. Again, I can't subtract yet. I still have an exponent. 4 to the second is 16 minus 5, which gives me 11. Okay, for your turn 3, what is another method to evaluate? Instead of each, I want you to pick one expression shown above. So I want you to go ahead, pick one of these 4 and do it a different way and tell which method you preferred. The way we did it in the example or the way you did it. Okay. All right. Ooh, stepping it up a notch. The rules for converting between radicals and exponents is the same whether it's numbers or variables. So now we're going to throw in some variables. Okay, and we need to simplify them. Simplify means getting down into the smallest possible version. Okay, so for this first one, I will tell you, for all of these, there are so many different ways to do them. It all depends on what you do. What you do first, what you do second. So when you're comparing your work to, say, my work or somebody else in the class's work, your work might look completely different, but that doesn't necessarily mean that either of you are wrong. Okay. So you're always one looking for that final answer. Really, if you simplified it accurately, both your simplified versions should be the same. Okay. So just because you might do it a different way than me does not mean it's wrong. Okay, so first I'm just going to show you one way of doing all these problems. Okay, so for this first one, the first one I'm going to notice is I'm going to rewrite this to show that for sure this is a multiply. This is 64 times y to the second to a power. So since I have a multiply, I'm going to go flip back a couple pages and we're going to look at that properties. Oh, one more. Okay, and if I have a multiply, okay, with an exponent, that exponent goes to each thing I'm multiplying. So that tells me that this exponent of 3/2 is going to both the 64 and the y to the second. So I'm going to rewrite it that way. 64 to the 3/2 times y to the second to the 3/2. So now I'm going to deal with the 64 to the 3/2. Okay, so this is just like those last examples. That 2 is the radical, so that tells me, and I know 64 is a perfect square. So I'm going to rewrite it as the square root of 64 to the third times. Now this uses that power to a power, the next part. So I need to take 2 times 3/2. A power to a power, you multiply the exponents. Kind of out of room here, so we're going to bring it up over here. The square root of 64 is 8. So I have 8 to the third times, when I take 2 times 3/2, 2 times 3 over 2, that gives me 6/2, which is 3. So now I need to take 8 to the third. Okay, if I don't know what 8 to the third is, I can grab my calculator, multiply 8 3 times. Or if you don't know this trick, 8, the to the button right above the divide is that to the button to take 8 to the third. It's 512. Okay, so 8 to the third is 512 times y to the third, which then we tend to drop the multiply sign and write it as 512 y to the third. Ta-da, we're simplified. Okay, next one, part B. Okay, this one is very similar to that last one, but I'm multiplying 3 things because that's 4. Again, be careful. That's 4 times x to the third. This 3, how exponents work is they only apply to the thing directly in front of them. This 3 only goes to the x. This 5 only goes to the y, except if there's parentheses. This 1/3 goes to all of it. Okay, so I'm writing this out. Oh, that multiply sign looked weird. Times y to the 5th to the 1/3. Very similar to the last one in that this would be 4 to the 1/3 times x to the third to the 1/3 times y to the 5th to the 1/3. Okay. 4 to the 1/3. 4 is not a cube. Again, the index of this now is 3. 4 is not a perfect cube. So there's really nothing I can do with that. Okay. The next one is 3. I would take x to the, so there's really nothing I can do with this guy. He's going to kind of follow along. 3 times 1/3 is 3/3, which is 1. So this is just x to the 1. Times, this would become y to the 5 times 1/3, which is 5/3. Okay, 5/3 is larger than 1. When you get an exponent like this, like 5/3, I can rewrite that, okay, and in a little method called, it's called simplifying the radical, we won't worry about a name, okay. We can simplify that guy down because 3 goes into 5 more than one time, but it doesn't go in for sure twice. So I'm going to take this 5/3 and we're going to split it up into a whole number because 3 goes into 5 once with how many remaining? 2 plus 2/3 remaining. So 1 plus 2/3, because this would be 3/3 plus 2/3 is 5/3. Okay, 3/3. So we can split this up into y and 3/3 times y to the 2/3. Again, using this, that 2 pages ago, that's using this property. Okay, a to the m times n. Okay, because how that's useful is y to the 3/3 here is just 1. This just becomes y to the 1 times y to the 2/3. Okay, don't forget we still have this x to the 1 and 4 to the 1/3. So the only thing that still has exponents are these two guys. So we'll pull those together. So let's put our x times y first. And then we have 4 to the 1/3 times y to the 2/3. Both their indexes are 3. So I'm going to write them as, not equals, as the cube root of 4 to the 1, y to the 2nd. Okay. I know that's a lot, and this is kind of one of the slightly harder problems that you'll do, but I wanted you to see this method before we kind of went with it. Okay. This next one is slightly different because they give it to us as a radical. They give the square root. We're going to rewrite that radical. We know the square root is the same as 2 to the 1/2, so we're going to write it that way. 20 times x to the 3rd times x to the 2nd, 2 to the 1/2. Okay, so this becomes 20 to the 1/2 times x to the 3rd to the 1/2 times y to the 2nd to the 1/2. Okay, 20 is not a perfect square. Okay. Again, remember our perfect squares, 2 to the 2nd is 4, 3 to the 2nd is 9, 4 to the 2nd is 16, 25. Those are our perfect squares. And how we know I'm dealing with squares is because, of course, that and the square root. Okay, so 20 is not a perfect square, but it has a perfect square in it. 4. 20 is equal to 4 times 5. So I'm going to rewrite it that way. 4 times 5 to the 1/2 times, this would become x to the 3/2 and y 2 times, that just becomes y to the 1. That one's nice. Okay, so we need to do this same process with this like we did over here, like we did right here. I need to split up my 3/2 into 2/2 plus 1/2. So it's x to the 2/2 times x to the 1/2. Oh, that should be 2/2, not 2/3. Again, 2/2 is 1. So x to the 1 times x to the 1/2. We still have y to the 1 right there. Again, if it's an exponent of 1, we don't tend to write it. Okay. And this next one now, I'm going to use that property that tells me that this exponent goes to both of them. 4 to the 1/2 becomes the square root of 4 times 5 to the 1/2, which is the square root of 5, times x times x to the 1/2. Actually, let's back it up. I'm going to just do the square root of 4. I'm going to leave 5 to the 1/2 times x to the 1/2 times y, because these aren't perfect squares. Let's leave them. The square root of 4 is 2. And then I'm going to write everything else that does not have an exponent, any of that crazy exponent, an x and my y from here, x and y. And then now we have 5 to the 1/2, x to the 1/2. Since these both have the same exponent, I can write them as 1 square root of 5x. So I'll have 2 times x times y times the square root of 5x. Okay. All right. Now, last your turn. I want you to evaluate that, the square root of 36, x to the 16th, y to the 36th. But I want you to do it 2 different ways. Okay, I want you to go ahead and do it 2 different ways and tell me which method you prefer and why.